All right, guys, I'm going to try and go through these homework questions as quick as I can because you submitted a lot of them. All right, starting with question 4 in 7.2, asking you to do a confidence interval. I set up a really quick, easy Excel spreadsheet. What I'm going to do is when I'm done with all of this, I'm going to upload this Excel sheet to either Canvas or the Google Drive so you guys can just copy the formulas. But basically this is what we're doing here is we're using this formula. It's the confidence dot T, and you have to do dot T because we're working on the T distribution, right? We're only going to use the normal distribution when we're dealing with proportions, because proportions live on the normal curve. The normal curve is also when we're dealing with means, but only if we know the standard deviation of the population, not our sample, right? So we almost never know that. So when in doubt, use T because you'll almost never know the standard deviation of the population. So if you're unsure of 99% of the questions you're going to see, if they're dealing with the mean, then we're going to use the T. So it's going to be equal confidence dot T. And then in fact, I'll type one in here and you'll see what it tells you. The nice thing about this is if you just double click on it, it tells you what you need. You need alpha, comma, standard deviation, comma, size, right? So that's what I have here. I've got N as my size, standard deviation, and my alpha level. And that's how we can compute this one. Darn it. So on this one, I'm just asking it to use those three numbers. And the reason why I set it up this way is because I'm sure there's going to be more than one question that's going to have the same, kind of setup. So all I have to do is just change the numbers and then I can answer the next question. Oops. So this one gave me a mean of 101.2, right? Gave me a standard deviation 21.1, told me my sample size was 20. It wanted me to compute a 90% confidence interval. So there's my sample size of 20, my standard deviation 21.1, there's my mean. If I'm a 90% confidence interval, that means my alpha is always 1 minus my confidence interval. So 1 minus 90% leaves me with 10%. There's my 0.1. I plug all that in. All I did here is I defined the lower bound as the mean minus this, because what the confidence thing gives you, it gives you the plus and minus amount, right? So you go from the mean and you add that amount and you subtract that amount, and it gives you a little interval that is centered around the mean. That's what a confidence interval is, right? Something centered on a measurement. In this case, it's centered on a mean. You can see that there's a little mu right here in the middle, so we know that's centered on the mean. So there's my mean in the middle. This is the mean minus the confidence, and then if we click on this one, we can see it's just the mean plus the confidence. So that's how I set it up. Then it's just a matter of rounding to the proper amount, and heck, if you wanted to, you could even do this and round to 1, and let it do the rounding for you, and then there are your results for this one. I'm not going to waste time with this crap. You guys need to figure that out on your own. We just don't have time. Okay, so on to the next one, number 5. Now we've got something with a set of numbers, and they want us to basically do the same thing, but with a set of numbers. Now we could just load those numbers into Excel and compute the mean and standard deviation of that sample and then still use this exact same setup. Or you could do it in StatCrunch. I don't care which, right? So I'm not going to waste time showing you how to do this one in Excel because it's the same darn thing. All you'd have to do would be to load these numbers right into Excel, run your summary statistics on it, and then change this number to whatever that sample size is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like 12. Change this to whatever the standard deviation is of your sample of 12, and then change this to the mean of 12. You're doing a 90%, so that still stays at alpha. And then these two numbers will automatically change to your new solution for this. It's still rounded to 1 decimal place, so we're all good to go. For those of you that want to do this stuff in StatCrunch, right? Open it in StatCrunch. Then you just go up here to T-stats, because again, we're running T-stats, right? One sample, and in this case, we have data, right? Bring this over. We want to do a confidence interval, change this to 90, hit compute, and there are the lower and upper limits, right? So we can type these in again, rounded to 1, So that's going to be 6.0, and then rounded to 1 is going to be 8.0, and we're all good to go. Now, on the previous one, right? So let's say you wanted to use StatCrunch for this one where we don't have the numbers. Well, you do the same thing. Go to Stat, T-Stats. Oh, wait, no, I got to start over, sorry. Go to Stat, T-Stats, one sample with summary. And here you just type in what you have, right? We have a sample mean of 101.2, standard deviation of 21.1, sample size of 20. We want to do a confidence interval of size 90, compute, and there we get the same answers of 93.0 and 109.4. So I think StatCrunch is going to be easier for you guys. Okay, so that's 4 and 5. 6 is probably pretty much the same thing, right? Again, exact same thing. We load this set of data into StatCrunch and then do the same thing. The only difference is now we have to change it to a 98% confidence interval. Okay. 7, construct 95, mean pulse rates. Again, same thing. We're doing means, right? We have to be on the T. So here's our data, load this in, and then run it. Just make sure that you're, running on the right thing because they want, males versus females. So they say do the mean pulse rate for adult females. So make sure you choose the column with the female data. Okay, 8, same thing, right? Load the data. 9 might be a little different. Let's take a look at. Yeah, see, 9 is asking for a sample size, right? So all the others were the same thing. We're just going to load the data and go, right? T-stat, one sample with data, blah, blah, blah. But you'll also see that when you go to T-stats, one sample, you have these two down here, power sample size and width sample size. Here they want you to figure out how big the sample needs to be in order to be within 3 IQ points, right? So that's all about width. So we're going to do width sample size. All right, this brings up our width thing, our calculator, whatever you want to call it. You need to change the confidence level to the right confidence level. Well, in this case, it's already at 95%. You need to change the standard deviation to what we have. We have a standard deviation of 10, right? We need to know our sample size. So it says find the sample size necessary. Okay, so that's what we need to solve for. So we're going to leave that blank. And the sample mean is within 3 IQ points of the true mean. So here's where it gets a little tricky. If we want to be plus and minus 3 IQ points from the true mean, then what's going to be the width of our interval? It's going to be 6, right? Because if we're plus and minus 3, we're 3 above, 3 below. It's a total width of 6. Hit compute. You'll notice that this goes to 5.9 and 46 because the way this thing works is if you tried to do it for exactly 6, the sample size would have been like 45.7 something. And you can't have a sample size of a decimal, right? So what it does is it always rounds up. So even if it was 45.1, it would round up because you need to be within that width of 3, right? Because if you rounded down, it would be a little bit bigger than 6. So in this case, our width is now going to be a little bit less than 3 in both directions. And we just say it is a sample size of 46. Okay, that's simple. Now, number 10, probably similar. Find the sample size using the range rule of thumb, right? So instead of using these computations, we're going to use the range rule of thumb. So you have to remember what the range rule of thumb is. So the range rule of thumb just tells us that the standard deviation is roughly 1/4 of the range. If you take the range and divide it by 4, that gives us a rough approximation of our standard deviation. So all that's going to change here is this is now going to be a 99% confidence interval, right? Because we have 99. Our standard deviation we have to calculate based on a low of 36 and a high of 116. So you got to do the difference between those to get the range, right? And that's 80. And then we cut that in, divide that by 4. So we have a standard deviation of 20. So remember, it's just range divided by 4. And then we want to find the sample size if we want to be within 2 beats per minute. So that's plus and minus 2, right? So that's a width of 4. Compute this, and it tells us 668. So let's see if we're right. Yay. Okay, so that's 7.2. Because this is all going to be the same thing. I'm not going to waste time showing you how to do something the same way again. All right, so let's move on to the next section. Okay, 7.3, we're dealing with the chi-square, right? That's what this thing is. That's chi-square lower, chi-square, well, left and right for lower and upper, but our book says left and right. We're dealing with chi-square because we're dealing with variances, right? The chi-square distribution is, we're doing the exact same thing. We're creating confidence intervals around a measurement. But instead of that measurement being the mean, where we're on the t-distribution, if we're now trying to figure out a confidence interval around a variance or a standard deviation, because remember, standard deviation is just the square root of a variance, so it's really the same thing. But we have to work with variances, by the way, with these things. And that's going to become a tricky thing when we deal with StatCrunch here in a second. But anyhow, we have to build things around that. We have to live on the chi-square distribution. It's a different shaped distribution, but the tools are all going to have roughly the same interface. So we're not learning anything new as far as StatCrunch is concerned. We're just going to a different place to kind of do the same clicking stuff. All right, so let's take a look at this first. Actually, we don't need to do these. You guys asked for 6 through 10, so let's go straight to 6 and see what 6 is asking for. Okay, so here we have to do a confidence interval for, you'll notice that this little symbol here is sigma, not sigma squared, sigma, so that's standard deviation. Sigma squared is variance. But here's where it becomes tricky in StatCrunch, because StatCrunch, and in fact, stats in general, we can only do computations. We can only work with the variances, sigma squared. So everything we deal with, we have to deal with variances, and then we have to square root things, right, to get results for sigma. So that's where you're probably getting mistakes on these. Okay, first things first, let's go ahead and load our data into StatCrunch and then see where we can go. Okay, really easy. Stat. See, now we're dealing with variances, so we do variance stats. We have one sample and we have data. See how that's very similar to what we were doing before? T-stats, one sample with data. Now we're doing variance stats, one sample with data. Okay, so we're doing what? We want to construct a 98% confidence interval population for which sample? Course evaluations. So here's course evaluations. This is the one we're using. We're doing a confidence interval. They want it to be in 98%, right? And then we hit compute, and you get these lovely numbers, right? And I bet you this is exactly what you did, right? You come over here and you go, oh, 2 decimal places, 0.21, right? 0.42, and it tells you, nope, you're wrong. And it even reminds you here that you have to take square roots, right? See all this big ugly stuff. You see how we're doing the standard deviation in the middle, and you see that we have a square root of all this stuff. Well, look at what this says up here. This is variance, and you see it's got sigma squared. So these limits are based on variance and not standard deviation. So what you have to do is you have to take the square roots of those two numbers. So take your calculator out, take the square root of those numbers, and then you'll get the right answer. All right, and then for the next one, you're just going to repeat the process, only you're just going to, go into options, edit, and change this to 93, compute it. And then remember, once again, you have to take these numbers and square them, right? So it's each one of those things squared and then round to the correct decimal places. Okay, so that should fix any problems you have with probably all of these, right? Because they're all going to be pretty much the same thing. Yeah, I mean, except for this one. I mean, 7, you're just literally just looking at a table. If you want to be 99% confident, it's this row. 20%, right, is what you want to be within, so your answer is 85. Okay, let's move on. Same question, and that's it. That's it for 7.3. Oh, someone said 4, 5, and 6, so I don't know why I was wasting time with 7 and 8. Sorry. All right, let's move on to 8.1. So 4, 5, and 6. Let me just double check I did all the right ones. I think I started with 6. Yeah, they're all the same thing, right? 4, 5, and 6 are all going to be the exact same thing. The problem here is you're going to have to remember to square those numbers. I'm sure that's what was tripping you up on those. Now, in 8.1, you can see that we're back to the normal curve for this one. And how do we know we're on the normal curve? Well, look what it tells you. Z equals 110. So if Z equals 110, we know we have Z scores, which means we're on the normal curve, right? So there's little things like that that'll give things away that can tell you, am I going to be running Z stats or T stats? I have students ask that all the time. Well, look at the question. Half the time the question tells you. Now, when it's on you should know what chapter 8.1 is because the book is, pretty obvious when you look at the chapters. But when it's on a test and they're all jumbled together, you can still kind of cheat by just looking at the question ID and knowing what chapter it's from. So that's why I gave you guys that list of formulas that are listed by chapter, because then when you look at chapter 8, you go, oh, well, it uses these formulas, which means I'm doing these types of tests, and it just helps you figure out which tests to run. But in any case, this is pretty easy, right? Identify the hypothesis test as being two-tailed, left-tailed, or right-tailed. Well, if your claim is P is greater than 1, right, that's an upper or a right-tailed test. Find the p-value. Well, that's where we have to actually run this thing, right? We have a z-score, and then we're looking for an upper value for a z-score. So we have to go to StatCrunch for that one. You could do it in Excel and graphing calculators and all that stuff, but these are just easier, right? Calculators. Now we're back on the normal calculator, right? Because we have a z-score. And we have a z-score. Because we have a z-score, we leave it at 0 and 1. We're looking for greater than, right? And we have a z-score of 1.1. And you're going, well, where does the 0.1 come in? Well, that's our claim. And then based on the claim, we got a test statistic, right? A test statistic of 1.0. That's what goes in here. This is the p-value associated with that test statistic. So we can copy and paste this here and then round to 3 decimals, which would be 136. And then obviously, if we're doing an alpha of 1%, this is bigger than 1%, so we fail to reject. And if we fail to reject, there is not sufficient evidence to support the claim, right? Because if we fail to reject, that means we're stuck on the null, and the claim is always the alternative. So that's how that one works. And again, I gave you guys that that Word document that has it helps you with these phrases, right? It's a little for. Let me just. I gave you this thing, and if not, just take a screenshot of it. It's pretty self-explanatory. The idea is that it helps you figure out. So in this case, our P was high. Our P was bigger than alpha, so we know we're in this one, right? And the claim was the alternative. We know the claim was the alternative because the claim was that P was greater than something, right? And remember, the alternative is always equal. So we know we have this thing here, and there is not sufficient evidence to support the claim. That would be the wording we're looking for, and that was the answer that we chose with that last question. Okay, all right, same exact question, only now we have 2.66. So we change this to 2.66, compute, right? And the only thing that changes now is this is a not equals. So because it's a not equals, it's a two-tailed test, right? Because we're looking for things that are on the high side or the low side. When we get this p-value, we have to double it because this is just giving us, and you can see in here, it's just giving us this little red bit on the top. But with a two-tailed test, we want to know the red bit on the bottom as well. So you basically have to double that and then put that number in for your. All right, as long as I didn't type it into my calculator wrong, 0.008 if you round to 3 decimals. Yay! Okay, so you just have to double it and then answer everything the same way that you would before. Okay. Assuming most of these are probably going to be the same thing. All right, so now we've got an alpha, original claim less than 57%, right? So that's going to be a left tail, blah, blah, blah. The hypothesis test results in a p-value of this, state the conclusion. Well, if this is my p-value and this is my alpha, right, then it's less than alpha, so we reject. We reject because the p-value is less than or equal to alpha. Remember, if the p is low, the null must go. Now, If we reject, that means the data is supporting the claim, and this claim, in this case, the claim is less than 50% would erase their personal information if they could, right? So that means the data supports that, right? So there is sufficient evidence, right, to support something because the data supports the claim. If there wasn't, if we failed to reject, then the answer would have been there is not sufficient evidence. All right, this is going to be the same question. And here we're just doing type 1 versus type 2 errors. Okay, so type 1 errors and type 2 errors can be a little confusing, but basically the idea is this, right? So remember, we have our standard bell curve. Now I know not everything is on a bell curve, but let's just pretend. And then we have our rejection region, right? We have whatever based on alpha, this is our rejection region. And if our sample statistic lands over here, then we reject, right? We reject the null. Well, alpha is always the size of your type 1 error. So a type 1 error is basically rejecting the null when we shouldn't have. Because remember, we said that when we get a result that's way out here in the tail, that just tells us that we were so far from the hypothesized middle, right? Whether it's, a mean or a proportion, or even if we're doing tests of standard deviations, it doesn't matter. Whatever the measurement was, and of course, if we were standard deviation, this would be a different shape, but again, who cares? The measurement that we get from our sample, right? So the mean that we get from our sample, or the proportion that we get from our sample, or the standard deviation that we get from our sample is so different from this hypothesized center that it lands way out here. We say to ourselves, well, it's so far from what the null hypothesis says it should be. We're going to reject this null hypothesis and say that most likely this is wrong and the population measurement is actually different. But that doesn't mean that that's actually the case. It could just be that the population measurement was in fact what the null says it was, and we just got a weird, rare sample. And so that's a type 1 error. It's basically rejecting the null when you shouldn't. So you reject the null when the null is true. That's a type 1 error. A type 2 error is just the opposite, right? So a type 2 error happens whenever you have a result that is here and you fail to reject, right? So a type 2 is you fail to reject when you should have, right? So since these are errors, you know that it's always going to be you do what you shouldn't have done. So a type 1 is you reject the null when you shouldn't have, and a type 2, I'll put a 2 up here, type 2 is you fail to reject when you should have, okay? So how does that wording work? Well, you rejected the claim that those who write with their left hand is equal to 27 when it actually is 27, right? Because here it says the proportion of people who write with their left hand is equal to 27. Do you see how equal to 27 would be the null? You reject the claim, i.e., because you reject the null, when you shouldn't have. And then you fail to reject the null, or in this case, you fail to reject the claim, right? When you shouldn't have, or when you should have. So those are type 1 and type 2. And the only thing that makes this one tricky is the null is actually the claim in this case. And you have to pay attention to that because the claim was that something is equal. Remember, an equal always goes in the null. So we normally try to set our claims up so that we don't claim that. I mean, the easiest thing to change would just be, I claim that the proportion of people who write with their left hand is not equal to 27. Then all of a sudden my claim would be the alternative and it would be much easier. But that's not what they did. They set it up here as the null. Okay, on to 8.2, the last one before this video gets way too long. Okay, in 8.2, we're just going to be doing a bunch of different hypothesis testing. And really, the three main hypothesis tests we're going to be doing in this class are we're doing tests about proportions, tests about means, and tests about variances or standard deviations. And they're all similar, but they use slightly different obvious tests, right? We're going to do tests about proportions. Test about means is almost always going to be T's. We would do Z's if we knew the standard deviation of the population, not sample the population. That almost never happens. And then tests about variances and standard deviations. So the question is, which of these three basically are we going to use? Well, It's a dead giveaway if you just look at this first question because it has P's here. So we're doing proportions. So we know we're doing proportion stats. Okay, well, what's the claim? To test the claim that the rate of inaccurate orders is equal to 10. So if the claim is equal to 10, that means we have to have equal and not equal. All right, so the claim is actually our null in this case. Now, if we want to actually run it, we're going to do proportion stats, one sample, and we don't have data, we have a summary. Okay, so number of successes. So we have one restaurant had 30 orders that were not accurate among 394 orders observed. Now, what are we testing for? We're testing that the rate of inaccurate orders is equal to 10%. So you see how inaccurate is the thing we're testing for. So that is our success. That's where this gets confusing because success, you think of, well, that would be an accurate order, but that's not what success means. Success means the thing from our sample has the characteristic we're testing for, and we're testing for inaccurate orders. So we had 30 successes, 30 things that were inaccurate. And then number of observations is the total. So that was all 394 orders. We're doing a hypothesis test. We have to change this to 0.1, and then you could change this to less than, greater than, or not equals, but ours is a not equal, so we leave that. This is what we would click if we were doing a confidence interval for other chapters. Then you just compute. Now, the test statistic is very simple. It's always the second to last thing you get. For this, it's going to be a z-stat. For the other thing, it's going to be a t-stat. And for standard deviations and variances, it's going to say chi-square stat. Okay, so this is my t-stat here. Copy that, paste it here, and yes, it matters that it's negative. 2 decimal places, so we're going to go 5, 8. And then the p-value is this one right here, pretty easy, right? 3 decimals, that's going to be 0.114, 0.114, and we're good to go. Do we reject or fail to reject? Well, where it's our significance level is 0.1. This is bigger than 0.1, so we fail to reject. It's either this or this. And if we fail to reject, there is not sufficient evidence to warrant rejection of the claim, right? In this case, so you can see that when you fail to reject, it always goes with there is not sufficient. You really kind of stop reading at that point because you know it's not. It's not going to be fail to reject, there is sufficient, right? Because those two go hand in hand. You fail to reject, there is not significant, right? So since there is not sufficient evidence, right, so it's going to be one of these two, to reject the claim, blah, 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 it appears that the inaccuracy rate is acceptable for the restaurant operations. Yeah. Okay. What? I must not read that right. Since there is not sufficient evidence to claim that the rate of inaccurate orders is equal to 10. Oh, it is plausible that the inaccuracy rate is 10%. Right. Yeah. There we go. All right. So read slower. All right, same exact question, right? We're doing P's, so we're going to do the exact same thing. We're doing proportions, only now what's our claim, right? We have to identify our claim. The politician claims that people don't really understand the stem cell issue and their responses to such questions are random responses equivalent to a coin toss. So he's basically claiming that the probability is going to be equal to 0.5. So therefore, we're going to have equals and not equals, it's going to be that one. And our claim is, again, our null hypothesis. And then all we'd have to do is go in here and change the number of successes and failures and run the whole thing over again. I'm not going to waste our time. It's the same question. Number 5, same exact question, P's again. And number 6, same exact question. All right, so they're all done the same way, guys. So 8.2 is all about proportions. You can see that they all have P's, so you're going to be using the same one. Stat, proportion, stats, one sample, most likely with summary. I don't think there's any in here with data. And then it's just a matter of put in successes, observations, make sure these match what they should be, right? This can change to a one-tailed test or stay at a two-tailed test. Make sure you change the number to match, obviously for this one, it would be 0.2, and then we'd have to figure out which of these is going on. And then you just got to figure out, where are our successes and where are our failures. Be sure to read the question because the success is just the number of things that has that characteristic. It's not necessarily the number of things that are good, right? So don't think of success as being a good thing in the real world. Think of it as just something that has the characteristic we're testing for. All right, that's it, guys. I hope this helps. Send me email questions if you've got them.